speed.
Right. Okay, so welcome back everybody to lecture 11, the penultimate lecture of the course. Oops. Sorry. And so today we're going to say something about optimization and linear regression. So optimization is something that you're doing on problem set 5, and there have been quite a few questions about how it works. So I thought it would be helpful to go through the sort of simplest possible example, linear regression, which probably a lot of people have already done, but you've probably done it by having some magic formulae that come out of some analytical calculation, whereas we're going to do it numerically, which is the simplest example of this whole field of, optimization, and a whole field called statistics, and another whole field called machine learning. So it's really fundamental in many areas of modern scientific research, scientific, dealing with data. What do you do with data? And it's fundamental in many areas. Okay, but first, we're going to finish off what we were doing last time. So last time we were talking about ordinary differential equations. So I've just discovered that I can actually highlight on this. So we were looking at ordinary differential equations last time, and in particular, the SIR model. So let's just recap that, in the problem sets, and indeed in the course in general, what we've been doing is sort of building up this model, so this mathematical description of this epidemic phenomenon. And in these models, we often have compartments. So the S, I, and R are different compartments, and we can transition between the different compartments at different rates or speeds, or with different probabilities, depending on whether we're in discrete time or continuous time. So last time we looked at the SIR model in continuous time described by a differential equation, right? So, so we're going to come back and do that again in a slightly different way now, and then we're going to look at how we can actually add uncertainty into that description. So I think this is very cool. In what we've been doing in the problem sets is start from an individual based model where we have a lot of people, and then we, because we have a lot of people, the stochastic nature of the model somehow gets averaged out. And when we then average over different runs as well, then we get something that looks smooth, and we've sort of tried to make this link between the average of this stochastic process and this quantity that we're calculating in the differential equations. But in order to use the differential equations but still represent some kind of stochasticness going on, we can actually talk about differential equations and solve them with uncertainties. So we'll say what that means. And that's the first thing we'll do, and then we'll talk about optimization after that. Okay, so I'm just going to go straight to the notebook. So it's I put the notebook up online, but I'm just going to work through it. So we're going to be using the differential equations package that Alan was talking about the other day. We'll use it in a slightly different way. But actually, the differential equation solver that you are writing in the homework in problem set 5, the simplest one, the Euler method, you can also do exactly what we're going to do with that. But I don't want to do it here because then you won't be able to do it on the homework. So we'll use the differential equations package instead, because, so one of the sort of philosophies of this course has been we're going to build everything up from scratch. So we are going to develop everything ourselves. We're going to write the code for everything ourselves to build it up, to see how everything works and how you program it, etc. To learn about software engineering practices, how you write good programs in software. That's a very important philosophy for us. But at the same time, we have to recognize that we cannot write, state-of-the-art differential equation solver. That will take you 5 years of work, and that's already been done. So there's not any point in redoing it, unless you can do it better, which you can't. So, because it's been done very well in the first place. And so we're going to use, so you have to recognize at the same point that once you have, at the same time, that once you have understood the ideas, the underlying ideas, then you have to recognize, people have invested a lot of time and effort in making these open source software packages that try and do state-of-the-art things, that try and implement the best algorithms in the best way. So we should actually learn how to use those as well as the sort of complement. And that's why we're using this package. Okay, so let me stop sharing this and start sharing the other thing. Okay. finally getting fluid at doing that. Okay, so here's the notebook, number 11, SIR-ODE model. So let's recall that, so this is reworked from this link. So there's actually a collection of recipes called on epidemic modeling with different languages called Epi Cookbook or Epi Recipes. Here's the link. And one of the languages is Julia. And there's various models implemented in Julia there. And including, I should also mention, let's just take a quick look over there. So here's what we're about to do. So I rewrote it in a way that I find a bit clearer. If you jump down here, you'll see that there's a SEIR model in Julia. And then if you jump even further down, you'll see simple stochastic models. So, so you can actually do SIR in continuous time, but still with individuals. And that uses exponential distributions and this thing called the Gillespie algorithm that we're not going to talk about. And you can do it in discrete time. And then somewhere, I thought there was a model that uses another package written in Julia. So let's just go straight there. So it's called agents.jl. So it's an actual modeling package for agent-based modeling written in Julia. And they've just released version 3, which does, you can do modeling in continuous space. So you can have these agents moving around in, not on a lattice anymore, but actually in continuous space. And so they have some radius of interaction, and that's actually much harder to program. So they've already done all the work. So it's actually, you know, here's a simulation of these agents moving in space, and they're being attracted or something to particular points, which is spelling out agents.jl. It's pretty neat. So I encourage you to play around with that. You know, if you want to do more serious modeling. Again, it's the same idea, right? We could write this ourselves, but they've done a lot of the hard work already, so we should take advantage of that. Of course, if you think you can do something better than they can, then because it's an open source project, you can just go in, fork it, change the code, and make a pull request to propose a new solution. Okay, so there's a lot of very cool work being done in the Julia community, and you know, people make these packages available, and they try their best to document them, not always successfully. You know, it's hard to actually document your own package. Anyway, so let's go back to the, where are we? SIR model, yeah. So you can see my SIR model notebook. Yes? Can you see that? Yeah, okay, great. So let's just remember what we're doing. So we have these 3 differential equations. We're using the notation S dot equals ds by dt. So these things, S, I, and R, are the number of people in the population who are susceptible, infected, or recovered, or removed. But actually, we're going to work in the version of the equation where they're not the number of people, they're actually the proportion of the population that is susceptible, infected, or recovered. But whatever. Okay, so we saw that there's this product coming from these interactions of susceptible and infected people with a certain rate beta. So we saw that in the section on exponential distributions that the rate means a probability per unit time, that when an I person, an infectious person, touches or interacts with a susceptible person, what's the probability that they transmit the disease? It's probability beta per unit time. So in a time delta t, it'll be beta times delta t, the probability that they transmit the disease. Okay, infection. Okay, so we want to implement this in differential equations. So Alan showed you one way of doing it with this sort of nice syntax. I'm going to show you a more, just a way that just uses normal functions. So here's this using differential equations package. So this takes a while to install. So if you haven't installed it, you'll have to wait a while for it to actually load. Sorry about that, because it has a lot of code. Okay, so what are we going to do? We're just going to write a normal Julia function. It takes 4 parameters. It has to take exactly 4 parameters, and they have to be in exactly this order. So this is the name that we give to our function that models the right-hand side of these differential equations. So I just called it SIR-ODE, but it actually modifies one of them. So it's going to have a bang, right? So it modifies the first argument. So the first argument is du. So u is the name for the vector of all the values of all the variables in our differential equation. So basically, what we're saying is that we're going to have a vector u at time t, which is s at time t, and I at time t, and r at time t. Right? So we're going to write everything in terms of a vector, which is just the values of all of the variables at that particular moment in time. That's my u. That's a vector. So I'm passing in a vector. I'm passing in a p. P are the parameters that I'm going to use. So here I've got a beta and a gamma. Those are parameters that I also have to pass into the differential equation. And then the time t. And then there's this other variable, which is the weird one, which is du. So what is du? It's another vector. And that is actually a vector that the differential equation solver is creating itself, and we are just going to modify it in place. So we're just going to overwrite whatever values were already there to start with. And the reason we're doing this, so you could, instead of doing that, you could create a new vector and return that new vector. There's also, I believe, methods that will enable you to do that. But it's often more efficient if you already have the vector, right? Because you already have the memory allocated. Allocating memory is actually slow. So reserving memory to store stuff in is slow in Julia, or in general, in computing. So if you already have one that's pre-allocated, that's already reserved in memory, it's cheaper just to write into that. And so that's what we're doing. And that's why we're modifying this argument. So what are we going to do? So we have this, we're passing in this vector u. So the first thing we do is just unpack that vector. And you can do that like this. So s comma I comma r, maybe I must make it a bit bigger. S comma I comma r equals u. That will just say s is the first thing in u, I is the second thing, r is the third thing. Right? And then same for p. P are the parameters, so I want beta and gamma, and of course I'm going to use Unicode in Julia. So just a reminder, you just write \beta tab. So you use LaTeX sequences to specify these symbols, and then press the tab key and it'll replace them with the Unicode characters. So now we want to define the differential equations, the right-hand sides, here they are, minus beta times si. So I just write that. I just write that right into the code, minus beta times si. Then plus beta times si minus gamma I, just write that in, plus beta times si minus gamma I. Okay. Of course, you don't actually need the plus. It's just to make it look a bit more symmetrical. And dr is plus gamma I. Okay. And then, so now we have these are the ds, the di, and the dr. So what does that mean? It means like the s dot or the ds by dt is that, right? So we don't say anything about the time step, right? When you're writing your Euler method in the problem set, you have to actually explicitly multiply something by a time step. But that's what the differential equation solver is going to do for you. Actually, it's doing something much more complicated with time steps arranged in a clever way so that it gives a much more accurate solution. And
you were pointing out how Nick Trefethen would discuss how if you can write it, you should be able to solve it, right? And so that's kind of what you're doing there. You're basically
exactly.
You're writing it and you're thinking.
And I'm just passing off the solving to somebody else, right? To somebody who knows about how to solve differential equations. And you can learn about those techniques, for example, in 18330 numerical analysis course. You can learn about what are the numerical methods that get you better, more accurate solutions to ODEs. Okay, and finally, we have to put those values back into the vector du, right? So one way of writing that is this, du dot equals ds di dr. If I just put equals here instead of dot equals, what will happen? I'm actually creating a new tuple. So I'm creating a tuple here. And then if I just put dot, if I just put equals instead of dot equals, it will set du to be this tuple. And that's not what I want to do. That's not going to do the right thing. I want to actually that's actually going to make du point somewhere. Well, it's a bit confusing what it's going to do. Let's not get into what exactly it does. But I want to actually write into the memory that's sort of pointed at by this vector du. And so that's with this dot equals, I can do that. Another way of writing that would be du, I index into du, and I get all of the indices, all of the components of du equals that. I think that should work. Okay, anyway, the sort of simplest thing to do is just put dot equals. Okay, so that's my differential equation function. That's the function that tells me what is the right-hand side of this differential equation, and it's written in such a way that it's suitable for these differential equation solvers in the differential equations.jl package. So do ask questions if you have any questions. So now we have to put all of the information in that we want to use. So these are some parameter values. I'm going to take beta, which is this infection rate, equals 0.1. I'm going to take gamma equals 0.05. Okay, I mean, these are just random parameters if you like, right? Later on, of course, we can change them. And so what we need is to put those into a parameters vector. So I just made a vector with those parameters, right? Using the standard Julia notation of square brackets. So there are various things you could do here that are more sophisticated, but we'll just use the standard Julia vector. And then I need initial values for all of the variables, right? Remember that a differential equation always needs, an initial value problem always needs initial values of all of the variables at time 0, or the initial time when you're starting the differential equation. So S0 is going to be almost 1, but there's going to be a small fraction of the population that's infected, so 0.01, and then nobody has recovered at the start. So then I make a vector of those initial values as well. And now I have this t-span here, the time, let's call it time span. So the time span is, I'm starting at the simulation at time 0, I'm finishing at time 200, pretty easy. And so now here, this is what we were commenting on last time, that there's this special type in differential equations.jl package called ODE problem, right? You have to get the capitalization correct. It's capital ODEP and then small letters, otherwise it won't recognize it. So it's making a new object of this type by passing in all of these things. So it's passing in this function, which has to have this bang. That is the name of the function. SIROD bang is the name of the function. There's vector of initial values, there's vector of the time span, and there's vector of parameters. It sets up a problem, right? So it's just creating the problem object. So we saw last time that if I do that and I run it, it will actually output in some nice way. It'll tell me, oh, this is an ODE problem. This is the type of thing. You know, these are the types of, this is the type of the time object, right? The times are going to be floats. The values that it returns at each time step are going to be vectors of floats, and etc. Okay, and now there's this magic solve command that will run an ODE solver. So if you don't give it, you can actually tell it which ODE solver you want to use. There's like 300 of them in this package. And so different solvers use different techniques and are suitable for different kinds of problems that have different kinds of behavior. But it will actually try and guess a suitable one for your problem. So I'm not putting one in, and it's just going to guess by analyzing sort of what happens when it starts to integrate, I believe, or yeah, I'm not sure exactly what it does. It'll analyze what's going on. And so when we solve that, it will run this ODE solver. So that's also called integrating the ODE. So there's an ODE integrator. It's the same thing, solving or integrating. It just means, as Alan was saying, find the functions S, I, and R that satisfy this equation. Find the functions such that S dot of t is minus b to S I of t for all t. Right, so it's a pretty complicated thing. It's solving this thing and it's giving me 3 functions as a function of time that are supposed to satisfy this differential equation. And of course, they're only going to satisfy it approximately, but they should satisfy it very well. So if I do that, I get some output. So it's outputting the times at which it stored the information, which I actually specified with this save at. If I don't put that in, it will choose its own time as when it's going to save the information. And it'll do it in an adaptive way, and we're not going to go into the details. And then it gives me the vectors of each of the 3 variables, S, I, and R, at each of those time steps, at each of those time moments. These are the values that it computed for all of that. Okay, and then we can plot it. So it turns out that they overloaded the plot command from plots. You just pass in this solution object, right? So what this solution thing, what is it? So get ready for this. This is the type of that thing. So we're not going to go into the details, but basically you can see that this type has a zillion types inside, because there's all kinds of types of all the different kinds of objects that happened inside this ODE solution. So you can see that there are some floats hanging around. There are some ODE functions. There are some wrappers of gradients. There are all kinds of things in there. And the point is that here are some of the ODE solver names that it's trying to choose between. So it's just, so why is it doing that? It turns out that it does that because in Julia, so we'll see this in a minute as well, when you put in different types into the solution, it will actually compile a special version of your ODE code, especially for those types. And so you actually need to put the types in somehow so that it will be able to calculate it, to do it efficiently. but yeah, but you know, if you try and wrap your head around these things, it gets a bit complicated. Anyway, so they also defined how to plot one of these solution objects, which has one of these types. And by default, it'll just draw the solution as a function of time for each of the variables. And then I can put labels. In order to do that, I have to make a row vector. So I don't put commas here, I put spaces. That makes a row vector of labels, and it'll take each label separately for each of the different curves. And then we see that indeed we get our epidemic outbreak, which is, you know, a sudden increase in the number of, almost a quarter of the population is getting infected, or say, I don't know, a fifth of the population gets infected, and then the infection dies out. And if I do it for a longer time, we'll find that the number of infectious people goes all the way to 0 asymptotically. Okay, so great. So that's how you use this package. And now, of course, what we want to do is change the parameters. So let's just load up our favorite interact package, and we'll run it. So I'm just going to put an app manipulate. So I'm have this range from 0 to 2 for the 2 parameters. I just put it, you know, don't want any magic numbers. I just sort of defined that once, and beta and gamma are taking all the values from between 0 and 2 with some small time step. And this capital T is how long I'm integrating for. And remember that if I just put for something, comma something, comma something, it'll make 3 different sliders if I put those in a manipulate. If I just have a standard Julia for loop, it'll actually be a multiple for loop. So I've just copied exactly the same code that we already had, and this is what we get. So now I can just manipulate these around and see what happens. So, you know, if I put gamma very low, then the infection, which is the red curve, just dies out, right? But if I start decreasing beta, hello, is it doing anything? It's not doing anything. That's very annoying. Oh, whoa, whoa, whoa. That is very annoying. Okay, I could restart and try and get it to work, but you can just play with it on your own. Sorry about that. There's these problems with interacted, you know.
I've seen that too.
Okay, maybe, is it worth, yeah, let's just do it. So I have to clear all the outputs. Oh, the stupid thing is in the way. My goodness. Clear all the outputs, save, restart the kernel. Clear all the outputs, save, restart the kernel. And then run everything. So annoying. Sorry about that.
This is the reason why I say manipulate is both my favorite function, the one that I hate the most.
Yeah. So by the way, this solution object, the one we just looked at, is actually programmed so that it behaves like a function. What do I mean by that? If I put a particular value of t and I just treat it as if it were a function and say solution at like of t, it will actually return the vector of variables at that time. And that's true even if I put a time that is not actually in my list of times, right? So it's actually doing some interpolation. So it's fitting a function in between the value. So it's calculating values at particular time points, but it's actually also able to fit a function that passes through those values. And so I can just evaluate that solution at any t. And so it behaves as if it were a continuous function, actually.
Pretty impressive.
Yeah, it is very impressive. And so in the problem set, of course, we're not going to do that. That's too complicated. So what I said was just, well, we'll come back to that later. So is it doing anything? Okay, it's still compiling plots. I mean, oh no, it's not. It's still restarting the kernel. My goodness, what is going on? Why does this nonsense always happen? I'm trying to do something.
Okay, in that line, you had a plot and an ODE, so it might have been the compilation of both the things. added together?
No, it said it was still restarting the kernel.
Yeah, I saw that.
Starting.
Oh, my bad.
No, you're right. You're right. It takes a long time to compile both of those things. Yeah, sure. But it's just, it seems to be really struggling because it's just still restarting the kernel. Oh, that's really frustrating. Let's just quit this. Okay. Okay, so while we're doing that, let's move on to the next section. So what about calculating with uncertainty? So as I was saying, so, you know, suppose we're trying to model a real population. And at the start, we think that we know how many people are infected, but actually we don't, right? So there's huge debate right now about, are the numbers that are being reported, do they bear any resemblance to the actual numbers, right? How many people are actually infected? We have no idea because we have not actually tested enough people. You know, basically you have to test a representative selection of the population who you think are infected or not infected to actually work out how many really are infected. So first of all, you have to have a decent test, and then you actually have to, you know, do some good statistical sampling of the population. And so basically we have no idea how many people are infected, or well, not no idea, but I mean, we have, you know, some amount of uncertainty in our value. So we have a measurement that looks something like this. You know, we have a proportion of the population, which is 0.1, but then there's some error on that measurement, right? It might be 0.1, or it might be 0.99, or it might be 0.10, 0.11, or whatever it is. And so we can actually write that in Julia as long as we load the relevant package, which is called measurements.jl. And so that will actually allow us to literally write this piece of code, right? So once this all loads up, so there, okay, this is actually working. Let's see if the interact works. We can actually write this piece of code. So this symbol here, okay, there we go. Let's see if it's now going to do anything. Okay, hooray. So yeah, so we can change these parameters. So so as I move beta, you see that the sort of epidemic curve, I'm decreasing beta, and the epidemic curve just dies out immediately, right? So it turns out that there's this condition that beta has to be bigger than gamma in order to have an initial increase in the number of infected people, and in order to actually have an epidemic, basically.
So reducing beta is like, you know, doing things like wearing masks or having social distancing,
yeah,
or if we actually do get immunity, that also would reduce beta.
Right. So let's.
So you really can start to understand the value of doing that.
Yeah, exactly. Beta is the probability of transmitting the infection. So as Alan said, if you social distance or physical distance, you will reduce beta, and if we reduce it enough, hopefully we can just, you know, flatten the curve, etc. And this, I can change the t, and it'll, you know, to zoom in a bit, right? So, yeah, so it's pretty cool to be able to do that so easily, you know, once you've restarted your kernel 17 times. Okay.
That's why it's both my favorite and my most dreaded.
Exactly. So here is t equals 3.05, which is not in my list of times because I'm storing times only at every 0.1, and I can just immediately evaluate the solution at that time. Or, you know, t equals pi, right? Is that going to work? So pi is this special number in Julia, and I can actually evaluate the solution at time pi because it's just interpolating with some smooth function.
Are people like oohing and ahhing at this? Like, you know, I mean, or, you know, maybe the people who will watch it later. I mean, the very concept that you're doing some sort of discrete calculation, and yet somehow you can magically think of it as a continuous function.
Right. Yes, there's a lot of, you know, there's a lot of interesting maths going on behind the scenes here that you should learn about in 18330. Okay, so let's do calculation with uncertainty. So we'll load this measurements package, measurements.jl, and now we can literally type this. So how do you type this? It's actually \PM +- right? And then you type tab. That will give you this symbol plus or minus, and that's the symbol that they use in this package measurements.jl to represent this uncertain quantity. So what are we saying? We're saying x lies in this range from 0.1 minus 0.01 to 0.1 plus 0.1. That's all I know about x. It's somewhere in that range. So now what can I do with that? I can do something like, oh, well, what do I know about 2x then? Oh, I know it's between, it's sort of average, its sort of middle value is 0.2, and then the size of the range that it might be in is 0.02. So I can actually basically define new arithmetic operations on these objects. So in a minute, I'll show you how we might do that in Julia. And so, for example, x squared. So if you take courses in physics or engineering, you'll learn about error propagation, how error analysis, how do you analyze the error in x squared. And it turns out that basically what you have to do is differentiate and whatever. And so this will actually give you an error of 0.002 if you square x. So what you're doing is you're squaring the sort of main value of x, and then to calculate this, you do some calculation that we can look at in a minute. Okay, so let's just suppose that that's all been done, and we're just going to use the nice implementation in measurements.jl that does something clever to keep track of stuff, whatever. So what can we do? We can literally just now specify, okay, I don't know exactly the value of the parameters in my SIR model. I'm going to just give them an uncertainty and see what happens. And I'll just plug those parameters right into this differential equation solver. I won't change anything else, right? I'm not going to touch anything else. All I changed from the previous bit of the code was just to add these uncertainties and load this package. Well, in the other order, load the package and then add the uncertainties. And I can just run the code. And the amazing thing is that it works. So it's compiling the package or some functions right now. That's why it's taking so long. And you'll see that it can just calculate everything. So every single calculation in this differential equation solution uses these parameters inside, and the result, of course, will have, so what it's doing is basically propagating this new type, right? So I forgot to run this code, yeah, type of x. So this x, which is this plus or minus thing, is called is a type called measurement, and it's a measurement around a float 64. So that, the type, the sort of middle thing is a float 64, and the error is a float 64. But you can put other things in there as well. Anyway, so you have this new type, and the new type has all of these arithmetic operations defined on it, like times and square and plus, and those are what you're using inside your ODE solver, right? So if you think about the Euler method that you're doing in the problem set, basically what do you need? Once you've written that out, you need plus, you need to be able to add two things together, and you need to be able to multiply a number, the step size, by some value. And so once you have those things defined on your new type representing some new type of numbers, like these measurements, everything should just work if you program your code correctly. And one of the things that you need to do in order to program it correctly is to actually not say what type anything is, right? So, in other, if you come from other languages or whatever, you might be used to defining all your functions, to say something like, oh, I have my sort of Euler method, and my Euler method takes in some h. Oh, h, I know it's a float 64, right? And s, which is also a float 64 or whatever. And you would write it like that. But now we actually want to pass in some other type for s. And so this is, so if you restrict it like this, you will not be able to use these measurement types. So you actually just want to leave it without any type restriction. Or, you might want to just sort of put a very generic one like number or real or something. So basically in Julia, we are often trying to leave things as sort of less typed as possible, which is kind of surprising. Okay, anyway, so if we do that, we get a solution. So I haven't printed it out. And now let's just plot. Oh, well, let's print it out. So I get a solution, and it looks like this. So it's interpolating in these times. It's giving me the answer in these times. And look what the answers are. The answers are vectors of these objects, right? It's a vector of vectors of measurements. It's pretty amazing. So everything just works. Okay, so so when you try and put two Julia packages together and put the, use the types from one inside the other, that's called composing the two packages. And so Julia has very high composability. That's one of the main amazing features of Julia. This is one example. Of course, if you try and put some type in some packages, it won't work because the packages may have restricted themselves to use types that they were thinking about, and now somebody came along and put some different types in. And so often what happens is, in that case, you write to the author of the package and say, oh, I'm trying to use your package with my types and it's not letting me. Can you basically restrict less, make freer the types that you're allowing? And that's what happened, I think. No, I think in this case, it just worked from the start because they'd already de-restricted it enough. But often what happens is you have to sort of do a bit of work to just make it work for all these other types. Anyway, now what they also did was...
So there's now two ooh-ahs in this lecture.
Yeah.
The first was you evaluate something discretely and yet somehow you can run it on any continuous argument. And now all of a sudden, some package that was supposed to work on numbers suddenly can work for measurements, even if the person who wrote it was only thinking numbers.
Right.
Like, where does that happen in this world, right? I mean, it's always the case that, like, when somebody writes something, they only write it for what they were thinking.
Exactly. Yeah, so basically so Julia is sort of giving us this extra functionality completely for free, basically. We have, there's basically no extra work involved, and suddenly we can do these cool things. So one of the extra things that they did was, now I want to plot the solution, and a solution has these measurement things in it. So you just need to know how to plot a measurement, and we're just going to plot it with a little error bar of the right width, which is the measurement width. And so what do you get? You get this beautiful graph that looks like this.
Even the plot function is...
So even the plot. So here somebody did a little piece of work, right? They had to say, okay, if I have a vector of measurements, how am I going to plot it? I'm going to plot it in this particular way. But that's sort of the only extra piece of work that was required. And now you get this beautiful plot, which is telling you, if I have that much uncertainty on the initial, on these parameter values, of course, you might have uncertainty on the initial condition as well. Well, that's easy enough to add in, okay, whatever. You have to be a bit careful maybe, but let's just try it. And you just run it, and it gives you something very similar, right? And so what's this saying? If we, you can actually get an estimate, a confidence interval of how many people do you expect will have, will still be susceptible at the end. And it's, within this interval, and you see that the interval is pretty big. And so you should really not trust models so much, right? If people are just reporting this middle number, well, you have to immediately ask, well, what is the error? What is your estimate of the error on that measurement? And one of the ways of doing that is just put errors on all of your inputs to the model, right? And Julia just allows you to do that in this beautiful way. Okay, so how could we actually define that measurements type?
I'm starting to think that every model that's put in a newspaper should have these error bars, because then the public will stop saying they're wrong. I mean, or at least it's less likely.
Right. So they'll just say, oh, we really don't know much. Let's find out some more, right? Well, let's try and reduce the amount of error on the input.
That would be good for the public to say it much more than probably.
We're going to try and just rapidly define these things. So just show what it looks like. So struct my measurement, and we sort of have a sort of underlying, like what we could call a midpoint, or let's call it a midpoint. So the midpoint, I'm going to make a float 64. So of course, I just said that you shouldn't restrict your values. I might want to put other types in there, but that's a bit more advanced, so we won't do that. And then we will have a width, which is also a float 64. And so, well, let's call it a radius. Well, whatever. Okay, I can't redefine it. Let's call it a width. And then I'm going to do base.show. So this is to, so if I do my measurement of 3 and 1, it's going to print it out in this way, and I want to print it out in a nice way. So I need to overload this thing called base.show, which looks like this. You pass in this thing called an IO, input-output argument. That's just how you have to do it. And you put in an object of this type. So let's call it x, which is my measurement. So the way I'm going to define that is like this. What I'm going to do is print to this thing called this IO stream. and then I'm going to print whatever it is that I want to print. So what I want to print is a string, and I want to put in the value of x.mid, and then this plus or minus thing, and then the value of x.width. And that's all. And I need to close my quotes. End. And now if I do x equals my measurement of 3 and 1, I get this. Right, so that's how they print it out in a nice way. How do you enter it in a nice way? You actually have to define this plus or minus function. So it turns out you can use plus or minus in Julia. So the problem is if I try and define this, it's going to complain. But let's try it anyway and see if it complains too much. So plus or minus of x and y, I'm now going to sort of override the one from measurement. And I don't know if this is going to work though. I don't think it is. It's going to be a my measurement of with x and y in it. Yeah. Okay, so let's put measurements dot that. I need this colon here. And now if I do 3 plus or minus 1, I don't know what it's going to do. Yeah, it's still using the one from measurements. Anyway, that's how you would do it if you didn't have this measurements package. Okay. And then what do I have to do? I have to define things like, oh, how do I add two of these things together? So actually I'm going to define, so I'm going to import the plus function from base, this sort of basic library in Julia. Base owns the plus function, and what I want to do is extend the plus function. So I want to extend it with an x, which is of type my measurement, and a y, which is of type my measurement. So I'm adding two measurements together. And how am I going to do that? I'm just going to add the components, right? So it's x.mid plus y.mid, and then comma. So I'm making a new object of type measurement, x.width plus y.width. Right, so if I have one measurement, which is 2 and 0.1, and another measurement, which is 3 and 0.01, and I add them together, then now it just adds the widths, adds the things, and prints it out in a nice way. So that's how these packages are made. There's nothing magical about it. You can just literally go straight to the package and look at how it's done. Of course, it's probably using more advanced Julia concepts that we haven't seen. Let's do it. At edit, measurement, at edit 3 plus or minus 4. So it's just going to take me straight to my editor in the corresponding line of this package where it defines how to do that, right? So let's just scroll up a bit and look at what it's doing. So yeah, so its measurement has this value and it has an error, and it's allowing any type t. This is what I didn't want to do just now. Instead of float 64, it allows any type t, but that t is restricted to be a subtype of what's called abstract float. So that includes big float and all kinds of other float types. And then, okay, it has another couple of things that are more complicated. And then you can just scroll down and see how do these things happen. So like at edit of 3 plus or minus 4 plus 3. So that's summing a measurement and a real number, and it gives me, so it's using this function called result, which is an internal function to the package, and it just adds the correct things in the correct way. So it's just doing exactly what we just did, but it's just a bit more complicated because it's trying to be more clever, right? So there's nothing special, there's nothing magical about these packages. They're just bits of Julia code wrapped up into a bundle. That's what a package is. Okay, any questions? That's all I want to say. Oh yeah, okay, that's all I want to say about measurements and ODEs. I just think it's so cool that this all works so nicely. And now I need to say a bit about anonymous functions that have been causing some trouble also in the problem set. So what is an anonymous function? So let's just analyze that phrase. So what is an anonymous function? Well, it's a function which is anonymous. What does anonymous mean? It means it has no name. So I think I mentioned this before, but let's just spend some time on it. So what does it look like? It looks like the following. X arrow, I make an arrow by a minus and a greater than sign. Yeah, I did mention this before. X arrow. So I'm actually going to tell you how to do one of the bits of the problem set because I know it's been causing some trouble. So X arrow 3x. So what is that? It is the function that maps a value x to the value 3x. Right? That's what it is. It has no name. right? I didn't give it a name. So look, I can actually do this. 3 maps to 3, x maps to 3x. That is a function. So let's apply it to something. Let's apply it to 10. What's that going to give me? Well, it puts 10 in and it maps it to 3 times 10. So that'll give me 30. So it just behaves as any other function. I just have to write it in this particular way. Now I could give it a name like g. G equals x goes to 3x. Now g is a function, right? So I can apply g to the function, to the thing 10. So why do I care about anonymous functions? And the answer is because in Julia, it's very common to pass functions. So in Julia, it's very common to pass functions to other functions. It is common to pass functions as arguments to other functions. And so it's useful to use anonymous functions for this. So now I'm actually trying to think of an example, and I can't think of a good example, of course, in this moment. Right, so, okay, so for example, so a function that takes other functions as arguments is called a higher order function. So a function that takes another function as argument is a higher order function. So I think somebody might have given me a good option. If only I could see the chat. Map, yes, this is what I had in mind. So we haven't really talked about map. So what does map do? So let's define a function f of x, which is 2x. Now I have suppose I have a vector v, which is 1, 2, 3. How can I apply f to each element of v? Well, we know that I can do f dot of v, but that's some special Julia syntax. What I'm actually doing is I'm applying f to each element of v, and I can write that like this: map f to v. So map applies this function to each element of v. Okay, but now I forgot that instead of 2x, I wanted 2x plus 1, right? So now I would have to go back and rename, like redefine this function, or maybe define a new function g or whatever. But instead of that, what I want to do is actually apply directly the function 2x plus 1 without giving it a name, right? So I would try this, 2x plus 1, map 2x plus 1 to v, and it'll tell me that it doesn't know, oh, yes, it'll tell me that it's trying to use some weird version of x that I defined before. Oh, no, it doesn't. Yeah, so x was a measurement, right? It's trying to use some previous value of x. I don't want that. I just want the function 2x plus 1. So what is that? How do I write that function? I have to tell it the function which sends x to 2x plus 1, right? What is x here? It's like a dummy variable. So it's the function which sends x to 2x plus 1. And that I can just write in this anonymous function syntax. So that's what an anonymous function is good for, when you pass things into other functions. Okay, so what are we doing in the homework? We have a function of 2 variables. You know, whatever, x squared plus y. And I want to have a new function. So I have a point a, b, like 1, 2. I want to have a new function that, so I want a new function where the value of y is fixed at b. So how do I do that? So probably some of you have already done it, and probably others if you don't know how to do it. So basically what I want is something like this: f of x comma b, right? This b is some value that I'm fixing for the moment. So I can just write f of x b, but what's it going to do? It's going to try and use some previous value of x. But so again, what I want is the function which, if I give it an x, will return the value of x at x and b. And so that is x maps to f at x and b. So if I call that g, now I can apply g to stuff. So g of 10 is 10 squared plus b, 102. And then in the homework, all you need to do is take this function, and that's the function that you're going to differentiate, right? So you have this function deriv, and you're going to apply it to this function. And that's the answer to one of the parts of the homework that is particularly difficult to get your head around, I agree. Okay, great. Any questions? If not, then we'll carry on with optimization, which is the other thing that's been causing trouble in the homework. So let me go back to sharing my tablet. Okay, so now we're going to look at optimization, and in particular linear regression. Okay, so what's the context? So we're supposing now that we have some data. So the data that we have in the homework is the data that you generated from a model that's stochastic, right? So you have some noisy data that has some epidemic outbreak, and we want to say, okay, if I think that that model, that is actually modeled by the SIR differential equations, can I fit the differential equation solution? You know, can I find the best parameter values, alpha and beta and gamma, sorry, in this SIR model that fit the data, right? That's what, right? So here are some examples of data that I might have in the real world: the stock price, jet noise, sales as a function of budget, length of the spring as a function of force applied, and you'll get some data and you know, some data which sort of have X's and Y's, and then some errors, and you know, it can be pretty messy. And then what we're going to try and do in this lecture is fit some best straight line through those data. Right. So, for example, in physics, we think that the length of a spring as a function of the force applied is actually a linear relationship, because that's what some theory tells us. And so we want to investigate, is that actually true? Or we want to say, well, which linear function is it? How does that depend on the spring or whatever? And similarly in the other fields. Okay, so, you know, there's just some philosophy about data and models that we've discussed quite a lot, so I'll just sort of skip over that. So we have inputs and outputs. We want to know, how do the outputs change when we change the inputs, right? So was there some relationship between the output and the input? So, but there's also some noise around, right? There's some fluctuations, there's some uncertainty, there's all kinds of mess. It's messy, the data, real world data is messy. So we need to take account of that. So what can we do? So this is the world of statistics, right? So I always thought that I never understood what the point of statistics was, because nobody ever explained this to me. But it's, you know, it's very clear once you understand, well, I have this data, but it has errors, and it has, you know, real world data is noisy. So now I need to really see, oh, well, how do those errors affect the, you know, if I fit a straight line and there are some error bars, well, actually I could fit another straight line that also passes through those error bars. And so actually I'm going to have errors on the fit as well. And that's what statistics tries to tell me. And then there's this other field called machine learning that's sort of the same as statistics and sort of not, because what they're trying to do is predict things, right? So they also have noisy inputs, but now they're trying to say this noisy input is a picture of a cat, and this noisy input is a picture of a brain tumor, right? So, so that's, you know, shares a lot in common with statistics, but it has a sort of different emphasis, which is this prediction emphasis. Okay, so what are we going to do? We have to model the data, right? So we can't do anything. Oh, well, there are some things we can do, but we have to have some idea of what the data might look like, right? So that's called a model, statistical model. So it represents a relationship between what we think the data is doing, like this straight line that we think is satisfied by this data on springs. So one of the simplest kinds of model is this linear regression model, which in my opinion is a really terrible name. The name linear is fine, it's a straight line, or more complicated linear things. But the name regression is just the worst name ever, right? Because it's just a really terrible name. Okay, because it sounds like, you know, I mean, regression is a very negative word in English, right?
I mean, was it Dalton who was talking about regressing to the mean, right? That the tendency of...
Yeah, there's a historical meaning. There's a historical reason why it's used, but it's just, sure, but it just doesn't mean anything these days. Right? It's just a word. It just means fitting. Yeah, so what does the word regression mean? It means we have some measurements, some quantitative measurements. We have some continuous input and some continuous output, and we have relating those two. So that's as opposed to if you have discrete categories, right? So you want to categorize this thing as a cat or a dog, then that is not regression. That's classification. That's a different problem. But regression is just means relating to continuous input to continuous output. Okay, so you can write this mathematically like this. So we think that we have some input X and some output Y. We think that the output is related to the input. How do we think that it's related? We think that it's related in a linear way. So you could either call this linear or affine, depending on which background you come from. So in mathematics, usually linear means that you pass through the origin, and affine means that you can shift yourself. And this is the case here, right? This B is a shift away from the origin. So it's actually affine rather than linear. And there's, but then there's this key part, which is epsilon, which is the fluctuations or noise or error, right? So we have, or uncertainty, or whatever you want to call it. So we have something where we're not certain and where we don't think, we're not expecting to exactly fit the data. We have some range of things, bars around the data or something, and the data are not going to exactly lie on this line. Right, so what do we want to do? So we reluctantly accept the fact, or you embrace it, depending on your point of view again, that there are these errors or noise. Okay, so we're going to do linear regression. So we're assuming here that we have, okay, so that I should put A and B as subscripts of the F. So we have a function f of A, this is f of x, f sub AB of x. So we have parameters A and B, right? So what are A and B? The whole point of the whole game is to find good A and B. So A and B that fit the data well, right? So of course we have to define what we mean by fit and what we mean by well in that phrase. So we have unknown parameters, so far unknown, and our goal is to find parameters such that the model fits the data. So what do we mean by fitting the data? So that's what we're doing on the problem set, right? So let's look at that. So let's just introduce some notation. So the data is going to be points. So we're just thinking in 2 dimensions, right? But you can extend this to higher dimensions. So we think these are the X, these are the inputs, and these are the Y's, which are the outputs. And so at some points, Xi, we have some input points, which are not necessarily equally spaced. So this is X1, X2, we have some data like this. Right? And that's what the data looks like, and they're just pairs of numbers, input, comma, output. And but in general, you might have inputs and outputs which are multidimensional. And so given those data, we want to fit a line through it. So here's one line, there's another line, there's another line, there's another line, there's another line. Which one is best? Yeah, so you can just eyeball it and say, oh, you know, the first one I drew is one of the best ones. But what does that mean? How are we going to define what best means? So yeah, so people these days talk about learning the parameters. So learning implies that there's some kind of process. So you start with some bad values of these parameters, and you gradually kind of converge to some better values, and that's what we're going to call learning, because it's supposed to somehow reproduce what happens in the brain. So this has absolutely nothing to do with learning in the brain. Let's not kid ourselves, right? Let's not pretend. Learning in the brain is a very interesting, very complicated process that nobody understands. And learning in a machine learning model is a very simple, obvious process that everybody can understand. And it has nothing to do with learning in the brain, but it's still called learning because people want to sound fancy. But basically, it's just what people used to call fitting, right? So you have some model, and in machine learning, the models are very, very complicated, but we are just fitting a model. What is fitting? It is finding the values of the parameters that best describe the data. Or maybe well, maybe not even best. Oh, so what does best or well mean, right? So how can we describe whether a function fits some data? So we need to say, well, how far away is okay? So again, we have our data, right? And then we have some function, and we will need to say, how far away is this data from this function? So there are different ways that we can measure that, of course. Right? So one way would be, okay, we can find the perpendicular distance of each of these data points from this line. Right? So this is perpendicular distance. But another thing I could do would be to find the vertical distance. So I should have drawn these data far further away from the line, right? So these things are vertical distance. So those are just two possible distances. Of course, there are zillions of other possible things you could do. So we're going to choose one, which is vertical distance. And we're going to say that the total distance of the data from this line is the sum of all of these vertical distances squared. And so the result of doing all of that is called a loss function or a cost function. So this is what the function that is measuring how far I am away from the data. So this is this common choice of loss function, but there are lots of others called least squares. So yeah, as I said, it's the sum of the squares of the vertical distances. So let's write that in maths. So we want a function, which is this squiggly L, curly L of A and B. A and B are the parameters in my straight line, right? So I have my function f AB of x is ax plus b. These are parameters. I'm not very consistent with the coloring, sorry. So strictly speaking, this should actually be, the parameters sort of belong down here, and then it's actually a function of the data, right? The data I'm putting in, but anyway, whatever. So how am I gonna calculate this thing? So because of what I just said, it's just this expression. It's, I take my input point xi, and I calculate for that point, here's xi. For that point, I have some data. That data is at height yi, and I have my putative, this line that I think I'm interested in, with values a and b of the parameters that describe that line. And now what I'm trying to do is calculate how far away that data is from that straight line. And I'm going to take the sum of all of those over all points and square them. So I'm going to square those distances and then take the sum of that. And that's going to describe some kind of measure of distance between the data and the line, right? And that's going to give me a number. Right? The sum of all these numbers squared is going to give me some other number, and that's the value of this function for those parameter values, this loss function. And now what do I need to do? What is best going to mean? It means I need to find the smallest value that this L takes when I change A and B. And that is an optimization problem. So optimization is a very important subject in modern applied mathematics and chemistry and engineering and economics and all kinds of fields, even physics. Actually, it's been important in physics for a long time, but they haven't really realized it yet. And machine learning is just optimization, by the way, basically. So yeah, so it's a huge field. And of course, we're not going to say much about it, but you're going to do it, in the problem set. So what do you have? You have some function as some complicated thing that looks like this, right? That's some f of x, or L of x, I'm calling it. Here's x, and it looks like that. So some kind of landscape with lots of wiggles. And what am I interested in? I'm interested in certain points on the landscape. I'm interested in the best value, which is the lowest possible value of this thing, right? This is called the global minimum. That's the best possible value, the least possible value. And then there are these other points which are called local minima. So they are points that are lower than anybody else in their little area. But actually, it turns out that if I go over the next mountain, I can get to a lower valley. Right? And so what I really care about is this. I would love to find the global minimum, please. But unfortunately, that's a very, very difficult problem. And so we're going to be satisfied by solving, sometimes at least, by solving a simpler problem, which is finding a local minimum. So what would a clever way of finding a local minimum be if we look at this picture? So if you've already read the problem set, you know the answer, but let's have answers in the chat. What would be a way of finding this local minimum? So if I start at some random place, like here, how could I find this local minimum? Like what algorithm would I try and do? Just looking at the picture, sort of, can you think of some physical system that will enable me to find this local minimum? Okay, so we don't have that much time, so did anybody send anything? I can't see my chat window. It's just totally, oh, there we go. No, nobody wants to give an opinion. Okay, so boring. Okay, so, well, let's think about this as a physical hill. This is like a profile of a hilly landscape, and somebody is standing at this point, and they drop a ball. Right at that point, they drop a ball. What's the ball going to do? It's going to roll down the hill until it reaches this local minimum. And then what it's going to do is, it's going to carry on up the other side because it has some momentum, right? Some inertia. But what about if the hill is covered in something sticky? Then it'll sort of gradually roll down the hill, and probably it'll sort of nestle in the local minimum. So that's exactly what we're going to do. So we're going to find a way to slide down the hill and sort of get stuck in a local minimum. And that's called gradient descent. And that's what you're doing in the problem set. So I'm not really going to talk about it much, but let's just set up this linear, what's it called? Regression problem. So there's another notebook which just has some fake data, right? So I should have taken some real data, but it's easier to just generate some fake data. And there's sort of some random scatter around, and we want to fit a straight line to this data. So what are we going to do? So a line, with ax plus b, right? So I want a line which represents ax plus b. So let's do that. So it's like a function of x, which is a times x plus b, right? So let's just plot the data. There's the data. I'm just going to choose some a and b, right? So let's choose a equals 0. So I have no idea what the right values are. So a is 0.1 and b is minus 0.3. Somebody in the chat said something. We can't see anything right now. Thank you. Resume share. Can you see something now? You can't see, yeah, you can see the notebook. Okay, good. Okay, so here's some data that I generated with. So this is a notebook that I put up. It just has this way to generate some random data, whatever. So this is what it looks like. We want to fit a straight line, right? So it's going to be something like that. Boom. That's going to be the best one. So here's a function that takes a line, and for a given x with parameters a and b. So parameters in Julia adjust parameters in a function, just normal parameters in a function.
I think your screen is frozen. Like do something, move your mouse or something.
I'm moving my mouse.
Yeah, no, it's frozen. Yeah, just try unsharing and sharing. Usually fixes that. Yep, now I see your mouse moving.
Okay, now do you see the notebook?
Yep, and the mouse moving over the notebook.
Great.
Yep.
Okay, so here's the data. That's what it looks like. I'm going to fit a straight line through it like that. Boom. Okay, so here's the line ax plus b is just a function that takes in an x, takes in the parameters a and b, and just calculates ax plus b, right? So this is like the most stupid basic function. But now we want to plot that. So I'm just going to choose some random arbitrary values of a and b, and let's plot the data. And now I'm going to plot on top of that, from 0 to 6 or whatever, this line. So how can I plot the line? The line is a function with parameters. How can I plot the line? Question for the audience. So what do I want to put in here? I want a function, but I want that function to be a function of a single variable x. And the answer is, hopefully, an anonymous function, yeah. So x goes to x arrow line of x with these values of a and b. So this a and this b are going to refer to these a and b up here. And this x is going to refer to this x, right? So this x is just whatever I'm inputting. And Julia will be able to, as we saw the other day, be able to plot this function on this range. And what we get is this, right? So clearly that is the lines down here and the data's up here. Clearly that's a terrible solution to the problem. So what do we want to do? We want to find a better one. So what are we going to do? Well, we'll do our favorite trick, interact. And instead of fixing these values of a and b, we'll do a manipulate. So for a and minus, I don't know, -1 to 1. As I said, I don't remember what the correct, what the values of the parameters should be, but we're going to find out what they should be, right? So I'm just going to manipulate with some range of values now. B in, sorry. So by hand, we're going to solve this linear regression problem. In other words, fitting a straight line through this data by hand. Of course, that's not really what we want to do, but that's the good first step. So the line is down here somewhere. And now I'm just going to fiddle with these parameters and see what happens and hope that interact works. And there he goes. So
in the old days, we just took a straight edge and plopped it visually down in the middle-ish.
Yeah, but this is much cooler. So so there we go. So it's something like that, right? But maybe if I change the slope a bit, then I can fit it a bit better by doing that, right? So now what I would have to do is define the loss function, which is this vertical distance from each point, right? So you can go and draw. I don't know if we really want to do that.
I would actually just sum up the squares and put it as the title.
Yeah, but I mean, that's what they're supposed to do in the problem set. I don't want to.
Oh, right. Okay, that's true.
But yes, that is what we should do. We should sum up the square distances from each. We should first of all draw the vertical lines from each point. We could do that because since I'm not gonna sum it up. Well, whatever. You can do it yourself. So draw the vertical lines from each data point to the straight line, and then those are the distances that we want to square and then sum up, right? And that will give us a number, which is the distance, a measure of the distance of the straight line from the data. And when we change a and b, that number is going to change. And so that's going to give me a function, and it's going to give me a function of these two input parameters, a and b. And now I want to find the global minimum of that, the least, which values of a and b, for which values of a and b does that function take on its smallest value? And the way we're going to do that is by sliding down the hill, right? And all of the details are worked out in the problem set, but hopefully this discussion makes it clearer what's actually going on in the problem set, right? So this is because, okay, but there's another point, right? So this is a function, this is a continuous function. So I can evaluate this function at any point. And the points that are interesting to me to evaluate it at are the points that come in the data. So there's an x here, x value here that has this data point, and I want to evaluate the function at that data point and take that vertical distance. And then at that data point and take that vertical distance. But in the problem set, what do we want to do? We want to fit the solution of an SIR equation. So the point is that here we have an explicit formula for this function. And in the question, I think it is 4 in the problem set, you have another explicit formula, which is a Gaussian function, right? A Gaussian PDF. You have an explicit formula with the parameters coming explicitly in that formula. And we can evaluate those functions at any point that we want. And so everything is sort of simple. But in the case of fitting the SIR model to the data, that's no longer the case because the SIR model output is a discrete sequence of points again. Right? It's just wherever I happened to solve the differential equation at. So if you're using the differential equations.jl package, as we've just seen, you can interpolate at any point and get the correct, and get a sort of continuous function out of the differential equation solution. But if you're writing it by hand, we're not doing that. And so what can you do? And so what I'm suggesting to do is, well, you have sort of data points, some certain number of data points, and you're trying to find the one which is closest to the given. So you have so you have this input data that's discrete data that's coming from your simulation, and then you have this sort of continuous function. Except you don't have a continuous function; you only have it at certain points. And so what I'm saying is, okay, if there's a point here and another one here, and I want to calculate the distance between this function and that data point, I'm just going to take the point that's here and calculate their vertical distance instead of that one there. And that'll give me some kind of approximation of this distance. So that was what the idea of the problem set is. So hopefully that makes it a bit clearer what's going on. So as I said, this is the simplest example of this really complicated field of really fundamental nowadays field of optimization. So in machine learning, you have something like a neural network. That is so let's just have 5 minutes on neural networks. What is a neural network? So we could actually do a bit on neural networks next time. I don't know if that was something that interests people. So what is a neural network? It's a network. It has sort of points and they're joined by lines. So yeah, we definitely should say something about networks in general. A network is just a sort of set of points, a sort of vertices, and they're joined in some way that represents some kind of connectivity relationship. And in a neural network, what you have are functions at each of these nodes, and the lines joining the nodes represent sort of more functions that you're applying to the output. So you have sort of neurons, which are just sort of simple functions that do a simple little task of classification, and you're connecting them up in some complicated way, and that's supposed to give you some much more, it's supposed to give you, basically it's just giving you another function. So it's giving you a function with a load of parameters, and when you change those parameters, the output of the network changes depending on the input. And so all the machine learning is find the best values of the parameters in this neural network that turn this, that fit the function which is turning this cat picture into the label cat and this dog picture into the label dog. Of course, the details of doing how you do that are a bit complicated, but basically it's just the same as exactly what we have here. So here, the cat picture has become a point in 2 dimensions. No, that's wrong. The cat picture has become a point in 1 dimension, right? The input is how much catness there is, and the y is like, do we think of it as a cat or not? So in the case of classification, we're just going to draw some kind of vertical line maybe and say if you're above this line, you're a cat. If you're below it, you're not a cat. So that's in a way simpler than doing linear regression. Okay, so that's in 5 seconds what a neural network is. Maybe we can go into more detail. But basically, the whole point is everything, a lot of statistics, a lot of optimization, a lot of machine learning is just write down a suitable loss function that you think will fit the data and then minimize it. And of course, sometimes you can do that analytically by hand, you're using calculus, but other times you just have to do it numerically. There's no option. So you can numerically find by going down the hill, or more sophisticated methods, of course, you can find the parameters that best fit your data, that this function is closest to the data. Okay, that's probably the end of what I had to say. Do you have anything to add, Alan?
No, that's probably a good place to stop. I mean, perhaps the only thing I could say is when machine learning just started to become like a big thing, I remember everybody saying to me oh, it's just regression, and as if there was as if telling me that was enough for me to understand machine learning, or
right.
I mean,
but I think it is important to say that there's nothing magic going on, right? It's just sort of falling down a hill, but the hill is now in 1 million dimensions. So that the magical thing is that we can actually do those calculations.
Well, I wasn't really imagining like there were like little people in the computer who were just like learning something, like.
But that's the problem with the word, right? It implies that there is something like that happening, and that's what I'm saying. It's really not. It's something much more boring in a way, right?
Is that what it comes down to? That when you actually understand it, it loses its magic? And
yeah, totally, yeah, I would say so.
It
loses its magic until you actually do the calculation and you actually can classify images as cats and dogs, and then it suddenly gets its fascination back, right? Even though you understand that all it's doing is this optimization thing, it's still pretty amazing that you can actually do it and it actually works.
Is flying more or less magical if you understand things about air pressure flowing on curved surfaces? I mean,
no, I mean, it is still magical. Yes, even when you understand that. Well, you know the story about was it Pauli? No, Fermi. No, one of Pauli or Fermi who discovered why stars shine, right? And I don't remember the story, but there's a good story about it. About you know, oh, it's such a beautiful night. Look at the stars shining, and he said yes, and I'm the only person in the world who understands why. Does that make it less beautiful that the stars are shining? No, it's still, you can sort of appreciate it aesthetically, but you actually, now it's even more beautiful because you understand the sort of physics of what's going on, and it's, you know, nuclear fusion.
See, in the modern world, you'd make a Zoom video, and then everybody in the world can understand it as well.
Right. Exactly.
Okie dokes.
Okay.
Sounds good.
Thank you, everybody.
All right. Take care, everybody.
See you on Monday for the last class.
Last lecture. Take care. Bye-bye.